Guys, welcome back to another session on Laplace transformation. So today we are going to take in another, that is our third session on Laplace transformation. So I'm going to take you guys back on the previous work we did so far on our last two videos. We treated on our last video we treated the Laplace of the exponential of at is equal to 1 divided by s minus a. So this is one of the standard solution of Laplace transformation. Then I gave an example and an exercise I asked you to work on. So today we are going to be looking at another standard solution of Laplace transformation, which is based when we are given a trigonometric function. So when we are given a trigonometric function, we'll be needing to understand how to take the Laplace of a trigonometric function. For example, now we're going to be taking another standard solution on Laplace transformation. So this is the third session on Laplace transformation. So I want you to follow me step by step. So very soon we'll not need to be going through all this process. So now let's take an example. So now let's take our third solution to Laplace transformation. So for example, we are asked to find the Laplace of the sine of 8. For example, find Laplace of sine 8. Now this is a general expression when you're having a constant a. Remember, a is always a constant. So we're asked to find the Laplace of sine 80. So now we're going to follow the same step we did or we followed based on our last two videos. So like I said, the general expression for the Laplace of a function is the integral from 0 to infinity of the exponential of minus st dt. So now let me write what I mean. So now let me write what I'm trying to say. So we're going to follow our last method we did based on our last two videos. So now let's find the Laplace of sine 80. Now this is our third solution to Laplace, our standard solution to Laplace questions. Now this is why I'm trying to make you understand this standard solution we are trying to derive so far, because it makes it easier for us to solve any Laplace transformation. So now let's work on this. So given this, now we have to find the Laplace of sine 80. Now we go back to our general expression for Laplace of a function, which says Laplace of ft is equal to the integral from 0 to infinity, right, of the function ft exponential raised to power minus st dt. So we are going to be substituting ft for sine 80. So Laplace of sine 80 is equal to the integral coming from 0 to infinity, right? So substituting ft for sine 80, we have sine 80 exponential minus st dt. Now if you look at this, we're having two functions of t. We're having sine 80 and we're having exponential minus st. Both of them are two functions of the dependent variable we are having here. So basically, when we are given the integral of two functions of when we are given the integral of two functions of the independent variable, we will need to apply integration by parts. Now like I said, so for us to solve this, we have to integrate it before we apply our limit coming from 0 to infinity. So let's integrate this stuff. So we are having integral sine 80 exponential minus st dt. Now like I said, these are two functions of t, sine 80 and exponential minus st. So we'll be needing to apply integration by parts. Now let's apply integration by parts. So integration, what's the formula for integration by parts? Which is integral of u dv is equals to uv minus v du. So based on the integral we are having here, so what is u and what is v? Now if we can remember our sequential order for finding integration by parts, it says the trigonometric comes before the exponential, right? Trigonometric comes before exponential. So our trigonometric, which says, so my trigonometric is going to take u and my exponential is going to take dv. So I'll call it sine 80, and my dv I'll call it what? Exponential minus st. So dv is equals to exponential minus st. So now, like I said, for u we are going to differentiate, and for dv we are going to integrate. So differentiating u, we have what? Du dt is equals to a cos 80, right? This is differentiating function of a function, right? Differentiating trigonometric of a function of function. At is a function, so which makes this when we differentiate cos, taking at to be another function, then differentiating that at, we have this. So I don't need to go about differentiating how to differentiate this. So differentiating sine 80, we have a cos 80. So moving over to dv, we are going to differentiate dv. So differentiating dv, we have what? Sorry, integrating dv, we have what? Integral dv, which is equal to integral exponential minus st, right? Integrating dv, which is integral of exponential minus st. So we have integral exponential minus st is equal to what? Exponential minus st divided by minus s, right? So now we're going to apply this in our integration by part formula. So I'm going to apply this on our integration by part formula. So applying this, what's my u? My u is sine 80 dv, right? Which is this. So which is equal to my u is what? Sine 80. My v is what? Exponential minus st divided by minus s. Integral. My v is what? Exponential minus st. My du is what? I get my du. So let's try it. So my u is what? Sine 80, right? Times my v is what? Exponential minus st, right? Minus integral, my v is what? Exponential minus st divided by minus s. My du is what? d is what? A cos 80 dt. Taking subject, making the u subject of formula, du becomes a cos 80 dt. So writing this, we will be having sine 80 exponential minus s, so divided by minus s, because this is v, right? So exponential minus s divided by minus s, right? Minus integral exponential minus st divided by minus s, a cos 80 dt. So this is how we're going to go about our integration by parts method. So I want you to follow this step by step. You might not need to, but I want to just, this is not actually important in improving, but I want you to see how we go about how to derive the Laplace of sine 80. So now let's move. Having this, just writing it here. So this is what we have, right? So now you see that there is also an integral sign here. Definitely we still need to integrate it again before we apply our limit. So we're going to integrate this part, leaving this other part out. We're going to bring out this other part and integrate it again. So bringing out this other part, we have this integral of, now before we integrate it, let's take out the constants, right? It makes it very, very easier for us to integrate. So before we integrate it, let's take out the constants. So taking out the constants, we have sine 80 exponential minus s divided by minus s. Taking out the constant, right? Taking out the constant, we have minus times minus is minus times minus becomes plus, right? So this becomes plus a over x integral exponential minus s cos 80 dt, right? So we're going to be integrating this part again. So integrating this part again, we'll be having integral exponential minus s cos 80 dt, right? This is what we are having. So integrating, we're still going to be applying our integration by parts method. So applying my integration by parts method again. So my u becomes this trigonometric and my dv becomes the exponential. So u becomes cos 80 and my dv becomes exponential minus st. So my u, which is cos 80, and my v becomes what? Exponential. My dv becomes exponential minus st, right? It's u and dv. So we're going to be integrating dv and differentiating u. So in differentiating u, my u, which is cos 80, du dt becomes what? Minus a sine 80, right? If I differentiate cos, I have minus sine, right? So this is what I'm having. So my dv, which is exponential minus st, integrating my dv, we have my v is equals to exponential minus st divided by minus s. So I'm having my du, which is minus a sine 80 dt, my v, which is exponential minus s divided by minus s. So I've got my du and I've got my v, right? So I just substitute here, which is equal to my u, which is cos 80, right? cos at times my v, which is exponential minus s divided by minus s. So exponential minus s divided by minus s divided by, sorry, minus my v, which is exponential minus s st divided by minus st, exponential minus st divided by minus s, right, times my du, which is minus a sine at. My du is minus a sine at. So this gives me cos at exponential minus s divided by minus s minus integral exponential minus st divided by minus s times minus a sine at dt. Right? So minus will cancel minus, right? So it is left with minus. So since I am having this, I'll just write it out. So this is what I'm having, cos at exponential minus st divided by minus s minus integral exponential. Now taking out the constants, we have a over s, right? Taking out the constant, which is a and s, taking out the constant, we have a over s exponential minus s times sine at dt. Remember, we integrated only this one. This is only what we integrated, right? And this is what we have. So we're going to be removing this part and bringing this part in this expression. So taking out this one out and bringing this one out into the expression. So I'm going to rewrite it in a more simpler, civilized manner so you can easily understand. So this is what we integrated, right? Then we had this. So I'm going to be substituting this. I'm going to be substituting this into this place. So we have sine at divided by minus s, right? Exponential minus st plus as. Now removing this part and bringing this one in, we'll be having open brackets cos at divided by minus s exponential times exponential minus st, right? Minus a over s integral exponential minus st sine at dt, right? Now, if you can remember our actual question, our actual question which brought us into integration by part was the integral of exponential minus st sine at dt, right? So now, since our initial question says let's take I to be integral of exponential minus st sine at. Now, as you can see that this is actually repeating itself, because this is what we were integrating at first, which we said make u to be sine at and make exponential st to be dv. So this is what we are actually integrating. So you see that when we are actually integrating it, the second step we are having that same integration here. So basically we just say take I to be exponential minus st. So since the initial integration we were saying integral of exponential minus st sine at, right, is equal to this, right? So this is sine at divided by minus s exponential minus st plus a divided by s, right? Open bracket cos at divided by minus s exponential minus st minus a divided by s integral exponential minus st sine at dt. Now, see what I'm trying to say is that at first we were integrating this part. We were integrating exponential minus st sine at, which we use integration by parts. So as time goes on, after integrating, you see that we are still getting this same expression in which we are having it. So basically, say let I to be equal to the integral of exponential minus st sine at, then we can easily solve. So replacing my integral of exponential minus st sine at with I. So we'll be having, replacing this, we have I, right, is equal to sine at exponential minus st divided by minus s, right, plus a over s, open bracket, cos at exponential minus st divided by minus s, right, minus a over s. So replacing integral of exponential minus st sine at dt with I, we having I, close bracket. So I'm going to rewrite this in a more simple. So we're writing this here so you can easily see it. So we're writing this here, we have I is equal to sine at exponential minus st divided by minus s plus as open bracket plus at exponential minus st divided by minus s minus as I close bracket, right? So evaluating. So multiplying through by plus sign, we have sine at exponential minus st divided by minus s plus as times as multiplied through this, we have a cos at exponential minus st divided by plus times minus, that's minus. So this becomes minus s squared, right? So plus as times minus as, we have minus a squared s squared I. So now we're going to collecting like thing, because this is I and this is I, this is I, and this one is having I. So bringing this one here so that we want to make I subject to formula, because we are looking for I. We want to make I subject to formula. So bringing this one here, we have I plus a squared divided by s squared I, which is equal to sine at exponential minus st divided by minus s minus a cos at exponential minus st divided by s squared, right? So making I subject to formula, we have I open bracket 1 plus a squared divided by s squared, which is equal to sine at exponential minus s divided by minus s minus a cos at exponential minus st divided by s squared. So now simplifying this will be having I, which is equal to s squared, right? S plus a squared. Simplifying this, 1 plus a squared divided by s squared, we'll be having s squared plus a squared divided by s squared. You can simplify it, it's like fraction. So which is equal to sine at exponential minus st divided by minus s minus a cos at exponential minus st divided by s squared. So now let's proceed. So now to make I subject to formula, we have to take this under this, right? So now making I subject to formula, we'll be having this is what we just previously used, so I wrote up this outer part. So making I subject to formula, we'll be having I is equal to, taking this under this, right? We'll be having sine at exponential minus s divided by minus s minus a cos at exponential minus st divided by s squared. So when this is coming over to this other side, we're actually taking the inverse of this. So when this is coming over to this other side, it's becoming an inverse. So this becomes s squared divided by s squared plus a squared. Now this is x squared plus a squared divided by x squared. So when this is coming over to this other side, because we need to make I subject to formula, so we need to eliminate this part. When this is coming over to this other side, it's coming over and turning into an inverse. So now, say if you have successfully carried out our integral, which is where I is equal to the integral of exponential minus st sine at from the previous question, and this is the question, this is the answer we have. So the next step is to take our limit. So taking our limit of this, which is equal to sine at divided by minus s exponential minus st minus a cos at exponential minus st divided by s squared, from limit from 0 to infinity, right? Now remember, our limit is went from t, which is equals to 0, to t is equals to what? Infinity, right? So there's no t here, so this is basically a constant. So we'll be having s squared divided by s squared plus a squared. So this is where we are going to be taking our limit from. Taking our limit from 0 to infinity, so times s squared divided by s squared divided by s squared plus what? A squared. So taking our limit, we'll be having, so we'll start with infinity first, right? So when t is equal to infinity, so when we put t, when t is tending to infinity, in this particular place, everything becomes what? 0, right? Because the exponential of infinity alone is 0. So 0 times every other one is 0. Exponential of infinity is 0. 0 times every other one is 0. So this becomes what? 0. So we're going to be having integral from 0 to infinity of exponential minus st sine at, which is equal to, so when t tends to infinity, putting it here, everything becomes what? 0, because the exponential of infinity is 0, here the exponential of infinity becomes what? 0, so 0 minus 0 is 0, so we're having 0 minus, so when t tends to 0, right, putting t equals to 0, so when this is exponential 0, right, now we did for infinity, put infinity inside this place, everything becomes what? 0, so when I want to carry out for 0, when t is equal to 0, when t is equal to 0, exponential of 0 is 1, so this is what we are having, sine at divided by minus s minus a. Now when putting t here, putting t, this is exponential 0, putting t is equal to 0, so we have exponential 0, and exponential 0 is 1, so 1 times cos 80, now t is also here, so this is cos 0, so cos 0 times this, everything becomes what? 0, right? So this is a times cos 0, which is what? 1, cos 0 is what? 1, so we have sine 80. First, let's carry out the exponential part first. So this is cos 80, exponential 0 is what? 1, right? So divided by s squared. Now we are still left with t here, right? Because we need to substitute every value of t, replace it with what? 0. Just like we did for infinity. Infinity replaced every value of t to be 0, every value of t to be infinity, every value of t to be infinity. Exponential of infinity is 0, so definitely every other one is 0. Exponential of infinity is 0, so definitely the other one is 0, so that's why we have 0. So minus for 0 when t is equal to 0, so replacing t is equal to 0 for the exponential, this is exponential is 0, which is 1, 1 times this we have this, exponential of 0, which is 1, 1 times this we have this, so we still have to carry out that same process, because we are still having variable t here. So replacing t here with 0, sine of 0 is what? 0, right? So we'll be having, so now this is t, right, and this is t, so replacing t equals to 0, so sine of 0 is what? 0, so we'll be having 0 minus, now do not forget our constant right here, so this is s squared divided by s squared plus a squared, so sine of 0 is 0, so everything here becomes what? 0, minus a cos, replacing t to 0, right, so cos 0 is what? 1, so we're having a divided by s squared multiplied by s squared divided by s squared plus a squared. So 0 to infinity exponential minus st sine at. So now 0 minus everything here, it becomes that same thing, right? So first we need to multiply 2 by minus sign. We are having minus this times this, that's minus 0, minus this times this, that's plus, right? Minus 0 times this is minus 0, minus this times that's plus a divided by s squared, right? All multiplied by s squared divided by s squared plus a squared. Now 0 plus anything is that same thing, right? So we'll be having, which is equal to a divided by s squared all multiplied by s squared divided by s squared plus a squared. So I'm going to write this, taking this up here, because remember this is our last point we stopped, so I rub up the top part. So taking this up here, we'll be having integral of exponential from 0 to infinity, right? The exponential minus st sine at dt, which is equal to, so we got it to be equal to a divided by s squared open bracket s squared divided by s squared plus a squared. So you can see that s squared will cancel s squared, right? So this gives me equal to a divided by s squared plus a squared. So we can see that the Laplace of sine at, right, which is equal to the integral starting from 0 to infinity of sine at, which is this is the same thing as this, right? Sine at exponential minus st dt, which is this, is equal to a divided by s squared plus a squared. So I've come to the conclusion of today's session, which says find the Laplace of sine at. So this is another standard solution to Laplace expression. So we are going to treat now about, let's say, 5 or 7 standard solutions to Laplace expression. Then you can solve any Laplace question. So this is one of them. So we'll be having, this is our third standard solution to Laplace expression. So this is our third standard solution to Laplace expression. So now we're going to take an example. We'll take one or two examples, then you really understand how to go about it. So now let's take an example. So we're having example 1. So we're having, since the Laplace of sine 80 is equals to a divided by x squared plus a. So let's take an example. For example, this has to find the Laplace of sine 5t. This is example 1. Now I'm going to leave you with one exercise so you understand how to go about it. So Laplace of sine 80 is equal to what? So since the Laplace of sine 80 is equals to a divided by x squared plus a, so where a is a constant, right? So comparing this with this, we'll be having, let's say, compare this with this. This is sine 80, right? Here my a is equal to what? 5, right? So since my a is equal to 5, so the Laplace of sine 5t is equal to what? Substituting a to this part, right? Now substituting a for 5, this is 5 divided by x squared plus 5 squared, right? Which is equal to 5 divided by x squared plus 25. So I hope you understand the arithmetic. So I'm going to take one more example, then I give you an exercise for you to solve. Example 2. Which says, find the Laplace of sine minus 6t. Now we all know that the Laplace of sine 80 is equals to a divided by s squared plus a squared. Hope you have jotted down that factor. So since the Laplace of sine 80 is equal to a divided by s squared plus a squared, right? Then here my a is definitely what? Minus 6, right? My a is what? Minus 6. Comparing this with this, my a is minus 6. So substituting a for minus 6, we'll be having Laplace of sine minus 6t is equal to minus 6 divided by x squared plus minus 6 squared, which is equal to minus 6 divided by x squared plus 36. So now I'm going to leave you with one exercise for you to practice. Now you can comment on this on the comment section below on the answer you get, so you can just take on to the next section. So we'll be having the Laplace of sine, that's number 1. Find the Laplace of sine 8t Now I want you to give you a quick revision on the previous standard solution we did. Second question says find the Laplace of 5. The third question says find the Laplace of the exponential 2t. So I hope you guys can actually solve this very, because it's very easy. So thank you guys for watching. Please subscribe.